Hello everybody, I am Valeria Stagno, a PhD student at the third year of the Department of Earth Sciences here in Sapienza, University of Rome. And unfortunately, I could not be there today, but I hope you will enjoy my presentation. And the presentation is entitled Tasting Portable NMR to Monitor the Effect of Paper Exposure to UV light. This work was done in collaboration with the Department of Chemistry, and the measurements were performed here in the laboratory of nuclear magnetic resonance of the National Research Council Institute for Complex Systems. And the aim of this work was to test the potential of portable NMR in detecting the aging effect of UV lights on paper. So we reproduced an artificial aging, and we monitored the effect of aging by using portable NMR. NMR is a nuclear magnetic resonance, and before showing my results, I would like to talk about this technique. We use the proton NMR. Proton NMR is based on the detection of hydrogen nuclei under specific conditions, so in the presence of a static magnetic field B0 and the presence of an oscillating magnetic field B1, which is induced by radio frequencies. And in this condition, it is possible to register a signal, which is the response coming from the hydrogen nuclei, called NMR signal. The NMR signal is defined multiparametric because it depends on different parameters such as the longitudinal and transversal relaxation time T1 and T2 and the diffusion coefficient, for example. So by studying the NMR signal, it is possible to provide a lot of information about the sample. It is possible to acquire a spectra which provide chemical physical information, or it is possible to analyze the signal and to measure the porosity of the sample, or it is also possible to exploit the imaging technique which allow to directly observe the structure of the sample through images. The advantages of NMR are that it is radiation-free and in certain conditions it is non-destructive and non-invasive. So we used in this work portable NMR. Portable NMR is a very small instrument because it is composed by a permanent magnet and a radio frequency coil which produces the excitation of the nuclei inside the sample. And it is possible to just lay the sample on the surface of the magnet. So for this reason, portable NMR can be used for measurement on objects of any size. And the signal, in our case, come from the 2 millimeter, the first 2 millimeter of the sample, and the signal intensity decreases in depth in the sample. So by using portable NMR, it is possible to, for example, perform measurement in situ on work of art of any size. And for this reason, portable NMR is non-invasive. So in this work, we used the portable NMR on a filter paper sample, and it corresponds to the Wattmann 44 paper, which is characterized by 100% of alpha cellulose and pore size from 2 to about 4 micrometers. We used an UV lamp emitting at wavelength of 365 nanometers and with a power of 36 watt. And by using this lamp, it was possible to reproduce the UV aging effect. We exposed the paper for 3 different times 48 hours, 52 hours, and 109 hours. And all measurements were performed under controlled environment with a temperature of 23 degrees Celsius and a relative humidity of 30%. And in this condition, the hydration level of paper was estimated to be below 5%. So we monitored the aging by using portable NMR. In our case, the instrument is characterized by a permanent magnet of with an intensity, a strength of 0.35 Tesla. And at this strength, the resonance frequency of the protons is 15 megahertz. And we compared our results by using a micro-Raman spectrometer. And about the portable NMR, we measured the relaxation time T1 and T2, which correspond to the longitudinal and transversal relaxation time, which have been acquired both on the unaged sample and on the aged for 48, 52, and 109 hours. So the sample of paper was just laid on the surface of the magnet. And then the results were compared with those obtained by Raman spectroscopy. Raman spectra were acquired in 4 different points of the unaged and aged for 52 and 109 hours paper. And now we can look at the results. First of all, the longitudinal relaxation time is shown in this plot, where we can compare the T1 trend for all the samples. And we can see that for the first 2 samples, so the unaged and aged for 48 hours, we have 2 different components of T1. And the first component is about 3 seconds for the unaged sample, and it decreases and then disappears for the rest of the samples, and it is associated with the free water. This is in agreement with the literature, for which the T1 of free water is around 3-4 seconds, and it depends on the hydration level of paper. Then for all the sample we measured the bound water T1, which is around 0.1 seconds, and in agreement with the literature, this T1 was found to be less than 1 second, and it does not depend on the hydration level of paper. In this work, instead, we did not detect the T1 of cellulose protons. In fact, the T1 of cellulose protons is equal to a few milliseconds, and it tends to 0 for low water content of paper. In our case, probably due to the weak sensitivity at low field, we did not detect this T1, or because the hydration level of our paper was too low, and so the T1 of the cellulose protons tends to 0 for low water content. And in this plot, we observed the shortening of the T1 of free water with the increase of the UV exposure time, while bound water does not change with the exposure time. About the T2, instead, we can see 3 different populations. The first is that of free water, and it decreases with the increase of the exposure time. Free water is inside the accessible sites of the amorphous cellulose. Then we have the bound water, which is divided into different populations: more mobile water in the amorphous cellulose and less mobile water, fast exchanging with the hydroxyls of cellulose. The first T2, which is the longer one, is associated with that of free water, and it agrees with the increase of the exposure time from about 40 milliseconds to 1.7 milliseconds, and this is in agreement with the T1 trend showed before. And about the T1 of free water measured at the longest exposure time, we can see an increase of the intensity, but this higher intensity is associated with a low dynamic, a low mobility of water, of this water component, and this can be explained on the basis of the increase of the number of accessible sites in the amorphous cellulose. But this water is characterized by a low mobility. Then we can see the two bound water components, and we observed a general decrease of these T2 with the increase of the UV exposure. But this decrease is more significant at 109 hours of exposure, and this indicates that the bound water lost its mobility. So the degrees of both T1 and T2 that we observed suggest that the UV exposure of paper for at least 52 hours affects the water dynamics and content of paper. And we corroborated our NMR results by observing the Raman spectra. So from the Raman spectra, we can see that the intensity ratio between the peak corresponding to the beta-glycosidic linkage stretching and the CH2 bending suggests a reduction of the beta-glycosidic linkage amount. And moreover, we can also see that the increase in intensity of the peak related to the amorphous arrangement and the broadening of the band over 1,500 cm to -1 indicate that more non-crystalline reagents are present in the aged paper. And so, in conclusion, we can say that in this work, a preliminary non-invasive protocol based on portable NMR T1 and T2 relaxation was tested in order to monitor the artificial UV aging of paper. Single-sided portable NMR detects the small changement in the water-cellulose interaction that are produced by the artificial UV aging process. Instead, Raman spectroscopy corroborates the NMR results and reveals modifications of the cellulose bonds induced by the UV aging. In future, to study the overall dynamics of paper decay caused by the UV light exposure, it is recommended to increase the exposure time. Thanks for your kind attention.